Welcome to the organic chemistry section. So with this video, we've got a new content section that gives you an idea of the things that we're going to be going through. So you can see here we're going to go through the introduction, formulas, isomers, functional groups, and so on and so forth. This section is going to be an introduction. We'll look at a little bit of the naming conventions, and we'll look at how to recognize and name each of these. And then we'll look at the tricks and tips in class. So first section is what is organic chemistry? So what is organic chemistry? Organic chemistry is the study of what known as carbon compounds. So we'll write carbon compounds here. So the idea is that we can break down chemistries and chemicals into two types. We can break them down into the organic and the inorganic. And what's the difference between these two? Well, to be really honest with you, the difference is an arbitrary difference. So what that means is that some people said these bunch of chemicals are organic and these bunch of chemicals are inorganic, because whilst organic compounds are basically the study of carbon compounds or compounds that have carbon and hydrogen in them, there are some other compounds that have carbon or hydrogen in them but are considered inorganic. So things such as carbon dioxide, carbon monoxide, cyanide, and carbonates. Yeah, these things have carbon in them, but they aren't considered organic chemicals. So really, there's a bit of a a scientific kind of arbitrariness to this. But honestly, you think of it as carbon and hydrogen compounds. Cool. So a little trivia for you guys is, why do they call it organic chemistry? They call it organic chemistry because before they got all these carbon compounds from living organisms. And these living organisms, in the 1800s or so on, they thought that living organisms had a special chemical inside them known as the vis vitalis, right? So the special life force that gave living things the life stuff and that non-living things didn't have. And they thought all these chemicals, they were sourced from living organisms. They thought they had the vis vitalis, therefore they called it organic chemistry. What you need to know are basically this. You need to know a little bit of theory information, and then you need to be able to understand and recognize different types of organic chemicals here, and then you need to be able to name the organic chemicals. These are the major three things that we'll do. So we'll look at the theory stuff a little bit more in class and have an exposure to the recognition and the naming today. Okay, so the first section we're going to look at here is on formulas. Basically, with organic chemicals, we need a way of representing the organic chemicals. So far, the kind of formulas that we've had are basically formulas that are written down on a piece of paper. So things like NaCl plus H2O forms blah 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 blah. So that's the kind of formulas that we've been exposed to so far. But organic chemicals are quite complex, so we might have a different type of way. We have a couple of different types of ways of representing these formulas, and the formulas are known as this. The first type is known as the molecular formula. Right? So this molecular formula is the exact same one that we saw in the calculation section, which involved what? Which involved us being able to write all the atoms that are present in a molecule. So, for example, I will draw you a molecule here. This molecule is going to be ethanol, right? Why is it ethanol? If we don't already understand that, we'll look at this and understand this by the end of this video. So this is what ethanol looks like. If we count up the carbons and hydrogens and oxygens here, we see there's going to be 2 carbons. So we write C2. And then there's 6 hydrogens, 1, 2, 3, 4, 5, 6. So that becomes H6, and then 1 oxygen, O. So the molecular formula simply tells us what atoms are present inside the molecule. So I'm just going to go ahead and write that down. What atoms are present. However, the issue with the molecular formula is that it does not tell us what the functional groups are. So it doesn't tell us anything about how the atoms are organized in 3D space. So no info on organization in 3D space. Okay, so that's the first one, molecular formula. The second one that you're going to be that's important for you to understand is known as the structural formula. Structural formula. Okay, and the structural formula is basically the formula where all the atoms and every single bond is written or drawn in the formula. So it basically shows all atoms and all bonds. So here we see that the structural formula is this formula here, where I've drawn out all the atoms in 3D space. So you see the carbons, the hydrogens, and the oxygens, as well as the lines that represent the bonds in between each of them. So the structural formula shows out all atoms and all bonds. So this is really good because you can see the 3D organization. So 3D organization of the atoms. So we can see what the functional groups are, what type of molecule, how the oxygens and hydrogens are organized. But it's really takes a really long time to go and draw. So it's very it's hard to write out on a piece of paper, and it's very impractical. So very impractical. So the third type of formula that you would want to be exposed to is known as the semi-structural formula. So it's known as the semi-structural or the condensed structural formula. And this basically shows the organization. So it tells us the organization of the atoms and what functional groups are present. So yes to organization of the atoms, plus yes to showing us what functional groups are present, right? And it's also very condensed. So most of the time we'll be using the semi-structural formula. And what does the semi-structural formula look like for this particular molecule? So if I see here, it's 3 hydrogens bonded to a carbon. So I'll write CH3 to represent this. So this CH3 represents this section here. And then I write CH2 to represent this section. So CH3, CH2, and then an OH to represent this section here. OH, right? Sometimes you might also see this as written C2H5OH. Both of these would be considered the semi-structural formula. Okay, so you can see that these 3 elements exist regarding the semi-structural formula. The formulas. Okay. One thing that I want you to know though is sometimes you'll see a molecule written something like this. So you might see CH, and you might see something written drawn as a wedge. So you might see a wedge coming towards you that's filled in, and that might be H, and then they might have a dotted wedge. So it looks something like this, Cl. Okay, so you might see molecules that look like this. I'll get you an example. Alright, so over here you can see that we've got a picture up, and we can see that this isn't exactly the same one as here, but we can see here that we've got our filled in wedge, so our COL colored in wedge, and then we have our dashed wedge. And the point with this is when you see these kind of wedges here, you want to remember that the colored in wedge is sort of like coming towards you. So it's a 3D representation, and the colored one is coming towards the page, and the dashed one is going away from the page. So the dashed one is saying that the CH3 is kind of like backwards, and the OH one is like forwards in front of the page, and the CH3 is behind the page. So this is just a way of representing what these molecules look like in 3D space. Alright, so the next section we're looking at is the section of isomers. The word isomers comes from the Greek root iso, which means same. So think of like isometric or isosceles, and this is bitch to spell, ISOSCELES, isosceles triangle. So you can draw a little triangle here. It has all the same sides. So an isomer is a situation where we have an organic chemical which has the same actual atoms inside it, but it has a different organization in 3D space. And it can be different in multiple types of ways, but the basic idea is that the isomers have the same atoms, okay? So if I have a molecule C6H12, the 2 isomers or 3 isomers or 4 isomers that you pick out will each have 6 carbons and each have 12 hydrogens, but they will have different organization in 3D space. Okay. There are 3 types of isomers that we need to be aware of. One is a type known as structural isomers, CTURAL isomers, and then there's another type known as stereo isomers. And within stereoisomers, there are two subtypes. You need to know about what are known as optical isomers, and you need to know about geometric isomers. Where are you? Geometric isomers. Okay, so 1 is structural, 2 is optical, and 3 is geometric. So what's the deal? Okay, a structural isomer, the first one that you need to know, is something that has the same molecular formula and different structural formula. It's very important that you remember this definition because it's a key definition that they will ask you again and again and again. So what does this mean? To answer that, I've got some cool pictures. Let's have a look at cool picture number 1 over here. So what is a structural isomer? A structural isomer is any of 2 or more chemical compounds having the same molecular formula but different structural formula. So you can see that this definition comes even in pictures I got off Google. If we have a look at the butane here, we see that there's 4 carbons, so it's C4, and then there's 4, 8, 9, 10 hydrogens, so H10. Over on the isobutane towards the right, we see there's 1, 2, 3, 4 carbons, and if you were to count all the hydrogens, you would also see that there are 10 hydrogens. So the molecular formula, the actual number of atoms in each of the chemicals, is the same, but the way that they're organized in 3D space, or the structural formula, is different. Here you can see that their 4 carbons are bonded to each other in a row, so the carbon's bonded to another carbon, which is bonded to another carbon, which is bonded to another carbon. Whereas with the one on the right, we see there's 3 carbons bonded in a row, and then one of these carbons here is bonded like a side chain to the main carbon. So the one on the left is just a straight chain, and the one on the right is a straight chain, but it's got a little branch in the middle like that. So we can see on the picture on the right over here, this is also a situation where we have isomerism. So the chlorine atom is bonded to the first carbon on this one. So let's say this is 1, 2, and 3. But on the picture on the right, the chlorine atom is bonded to the second carbon, or the middle carbon here. So they both have 3 carbons. They both have 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. They both have 7 hydrogens, and they both have 1 chlorine. So the the molecular formula for both of these is the same. But we see that the chlorine is bonded to a different carbon atom in each of them. So the 3D representation in space, or the structural formula, is different. So these are what are known as structural isomers. Okay, important section. Number 2 is optical isomers. Optical isomers are a type of a thing known as stereo isomers. And the way that the chem course wants you to think about it is that a stereoisomer is something where the actual atoms are the same, so the atoms in the molecules are the same, but the organization in 3D space, so the way that these atoms are organized in 3D space, 3D orientation, is different. Okay, so there's the actual atoms that it's composed of is the same, but the way that it's oriented in 3D space is different. So an optical isomer is a type of stereoisomer. So what is the definition of an optical isomer? An optical isomer is an isomer where we have a stereoisomer which differs by the placement of substituents around one atom in the molecule. Okay, so a stereoisomer which differs by the placement of substituents around one atom in the molecule, which means what? Which means if I have an atom of carbon here, let's say there's A, I'll put an A, B, C, and D, or maybe make this an X and D. So the carbon atom in the middle, and there's A, B, X, and D surrounding it. So a stereoisomer is when these things, A, B, X, and D, we don't know what they are, just random atoms, the way that they are organized around this carbon atom is different. And let's have a look at what this looks like. the concept that we need to look at is this concept of chirality. And what does this mean? A molecule or a thing is considered chiral if it cannot be superimposed. So chirality is like the property of not being able to be superimposed. So something is chiral, something is considered chiral if it can't be superimposed. Right? So if I have something like my left hand over here and I put it against the mirror, I will get my right hand. Okay? If I put my left hand and my right hand on top of one another, we can see that they don't form a neat superimposition on top of one another. Okay? Whereas if I get a milk bottle, which is symmetrical, and I put a mirror on it, I'm going to get exactly the same shape. So over here, when I put the two milk bottles on top of each other, they can be superimposed, whereas this one cannot be superimposed. So what's the significance of this? The significance of this is that we call these objects that cannot be superimposed chiral. So this is a chiral object. And the idea is that the chiral objects are objects that are not symmetrical, right? So certain types of not symmetrical objects, when you put them in front of a mirror and get their mirror image and put the mirror image on top of the original thing, they cannot be superimposed. So our optical isomers are chiral objects. So the point to bear in mind here is that optical isomers are chiral objects. So let's just write this again. So optical isomers are chiral. Okay, and chiral just means that it can't be superimposed. All right. So a chiral object can't have its mirror image be superimposed on top of it and make a neat image. And these type of objects are going to be non-symmetrical objects. Okay, so we could say that my left hand, I can't draw, but this is my one hand and this is my other hand, or whatever, and my left and my right hand, they are going to be optical isomers of one another because they are going to be consisting of the same things. They consisted of a thumb and a bunch of fingers. And when I put a mirror in between them, I get a mirror image. And if I put the two images on top of each other, I can't superimpose them. Okay, so concept is my left and my right hand are considered chiral objects and they are optical isomers of one another. So how does this apply to chemistry? Let's have a look at this picture over here. So over here, what I can see is that I have my left hand, my right hand, and I've got two different molecules here. And we can see that these molecules are consisting of the same things. There's this COOH thing in both of them. There's an R group in both of them. There's a carbon, there's a nitrogen, and there's a hydrogen, right? So they're both consisting of the same things. But we can see that when I put them, they're both a mirror image of one another, as you can see here. But if I were to superimpose them on one another, they would not be able to be superimposed. So these two things are examples of optical isomers. Okay, very good. But the next question would be, how do we actually go and determine what is an optical isomer and what is not an optical isomer? Okay, so how do we tell if something has an optical isomer or not? The way that we do it is we have to see whether or not this molecule is going to be asymmetrical around a certain point. Okay, so if it's asymmetrical around a certain point, it will have an optical isomer. So what is this? What's the deal with this? The deal is it has to be asymmetrical around a certain point. That means that if I were to reflect this molecule and make a mirror image of this molecule at this particular point in the molecule, it would have a mirror image that could not be superimposed on the original image. So this type of point, in other words, this molecule has to have what's known as a chiral center. So how to tell if something has an optical isomer? It has an optical isomer, if it has an asymmetrical point, which is known as a chiral center. Okay, so if something has an optical isomer, it will have what's known as a chiral center. A chiral center, for our intents and purposes, is simply when a carbon is connected to 4 different things. So this is P, this is Q, this is R, and this is S. So when a carbon atom in a molecule is connected to 4 different things, this carbon atom is considered a chiral center. So this is going to be a chiral center because P, Q, R, and S are 4 different things. So if we go back to our previous picture over here, what we can see that this carbon over here is connected to 4 different things. It's connected to this carboxy group, this alkyl group, the amino group, and a hydrogen. So you see 1, 2, 3, 4. So since this carbon is connected to 4 different substituents or 4 different species or 4 different groups, it's considered what's known as a chiral center. So if a molecule has a chiral center, it's going to have this like asymmetry between it, so that when I get a mirror image of it and make this molecule, this mirror image will be non-superimposable on my original carbon, therefore it will be an optical isomer. So to simplify it all a bit, what's the deal? Okay, optical isomer, how to tell if something has an optical isomer? It has an optical isomer if it has a chiral center. And what's a chiral center? The chiral center is a carbon bonded to 4 different things. Okay, so if there's one carbon that's bonded to 4 different things, that molecule will have an optical isomer. Okay, so if we have a look at this picture over here, we can quite easily see that this carbon here is bonded to 4 different things. So it's bonded to a hydroxy group, so the carbon is bonded to an OH on one side. On the other side, it's bonded to a CH3. On the bottom here, it's bonded to a hydrogen. And on the left over here, it's bonded to 2 carbons and 2, 4, 5 hydrogens, C2H5. So if we have a look at all the things that the carbon's bonded to, we can see that it's bonded to 4 separate different things. Therefore, as this picture indicates, this is considered a chiral center. Since it has a chiral center, it's going to have an optical isomer. Right, lastly, we want to look at the third type of isomer, which is known as the geometric isomer. Right, geometric is also another form of stereoisomer. So remember that the stereoisomer was a molecule that has the same atoms, but it's organized differently in 3D space. A geometric isomer only occurs when we have a restriction of the rotation of a molecule. So it occurs when there is restriction of the rotation of a molecule. So significance of this is what? Most of the time we have free rotation of the bonds in the molecule, but we get restriction when we have ring molecules and when we have double bonds. Okay, so the ones that we're interested in our chemistry course is going to be the restriction of rotation of a molecule in double bonds. So what do these kind of things look like? Well, the 2 types of this. Let's say we have carbon-carbon double bond and the other carbons connected on this side and this side, okay? And we have the same thing. We have a same carbon to carbon double bond, but the 4 carbons are going to be on this side and the 4 carbons are going to be on this side here. Okay, so in both of these molecules, molecule 1 over here and molecule 2 over here, there's 1, 2, 3, 4. Oh, whoops, I'll just draw another one here. Sorry. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, I'm just going to delete one of these. Whoops. Here we go. So the idea is that there's 9 carbons in each of them. Okay. Yeah, 9 carbons in each of them, and there's 1 double bond in each of them. So that's the same number of atoms. However, if we take a look at the molecule in molecule 1, okay, also just be aware that there would be hydrogens here and hydrogens here, a hydrogen here and a hydrogen here, and also hydrogens attached to all the other carbons, but I just won't draw them in to keep it a bit neat. So if we have a look over at molecule 1 over here, we see that the group of carbons, right, the group here is attached to is on one side of the double bond, and the rest of the carbons are on the other side of the double bond. So if I draw like a line here, we can see that the two of them are on different sides of the line. However, if I draw the same kind of line on molecule 2, we see that the group of carbons over here is on one side of the double bond, and what happens is the group on the other side of the double bond is, on the other side of the double bond is also on the other group is on the same side as the double bond. So we can see here that these two are on opposite sides. On the left and on the right, we see the groups are on the same side of the double bond. So these two are different organizations in 3D space. We call the first type a trans isomer. Right? Trans means across. Think of like the transatlantic steamers or like ferries. So think of the idea of transatlantic. So it goes across the Atlantic Ocean, right? Whereas here is cis. Cis means on the same side. Okay, so I just remember cis and trans, and then I know that trans is transatlantic, so it must be across from one another, whereas cis is the same side, so it has to be the other one, which is the same side here. So we can see that these two are going to be the geometric isomers. The last section we're going to look at is this idea of functional groups, the last section for this video. The rest will be covered in the next video. So functional groups are, the definition of the functional group is basically an atom or group of atoms which imparts chemical properties to an organic chemical. Okay, so remember we said that chemical properties right at our very first lesson was what a chemical reacted with. So the chemical properties of a chemical referred to what exactly could that chemical react with, okay? Because chemical change was chemical reactions, going from products to reactants where new chemicals are formed. So the way a functional group works is a little bit like getting a new USB port. So for example, in computer technology, there's a whole bunch of different cables and ports. Here we can see there's an Ethernet port here. I don't even know what these are, some other kind of port, and a USB port over here. So there are different types of ports that are available. And the idea is that if you go to your computer and you pay someone to add a new port in, or you install a new kind of USB port into your computer, that now allows you or your computer to access and connect to a whole bunch of different things. So let's say I didn't have a USB port and I just got a new USB port. So I got this new USB port over here. What could that let me do? Well, that could let me connect to keyboards, mice, gamepads, I don't know, satellite receivers, Bluetooth adapters, iPads, and blah blah. All these kind of things here are now within the jurisdiction of my computer, because now I can access and connect to all these things. But if I did not have a USB port, I wouldn't be able to do and connect to all these kind of things here. So the idea is that with organic chemicals, it's the same. An organic chemical might have something like, let's say we get ourselves a organic chemical, and it's a generic organic chemical. So we have just carbons and hydrogens. So we have our basic carbons and our basic hydrogens like this. And this on its own can't react with much, okay? But let's say we give it a snazzy new USB port. So there's a group known as a carboxy group. So let's say we connect a carboxy group. So the carboxy group looks something like this. So think of this here as a USB port, all right? And this over here as my basic computer. If I connect the carboxy group to my basic computer, what happens? Well, I'm just going to have to redraw it a little bit here. Let's take that over here. And then let's imagine that my carboxy group was connected to my computer like this, all right? So I'm just going to redraw it now. All right, and here we go. So now what's happened is that my organic chemical now has this functional group attached to it. So this functional group, when it's attached to this organic chemical, means that this organic chemical can now react with a whole bunch of different things now, because this carboxy group is like a USB port, which allows it to react with things like alkanols, which allows it to react with things like bases, and so on. Okay, so the idea is that functional groups are atoms or groups of atoms that impart particular chemical properties on them. They're like little add-ons that allow this particular chemical to now react with a whole bunch of different things. Cool. So the one point that we want to make here, though, is that when this happens, when we add a new, let's say, a new functional group to a molecule, it actually changes what that molecule is called and the type of molecule it is. So before, when it was just this plain Jane chemical here, this was known as an alkane. So it was a particular type of chemical. But once I added a particular functional group, so in this case, this functional group is known as a carboxy, and you probably would have seen this in year 11 group. Once we've added this carboxy group into this chemical can no longer identify itself as an alkane. Because it has a carboxy group, it is now going to be called a carboxylic acid. Right? So the point isn't to tell you about carboxy groups and carboxylic acids here, even though that's important. The point is to say that the identity or the family, right? The chemical family in which the chemical belongs to is determined by what functional group is present. Okay, so if we clear the screen, let's take a look at the principles here. All right, so a functional group is something that imparts chemical properties to the chemical. Chemical properties refer to what the chemical reacts with. Chemical reacts with. Okay? And when the functional group is given to a chemical, it will also change and determine what the family of chemicals that this particular chemical belongs to. Does it belong to the alkane type of chemical? Does it belong to the acid type of chemical? Does it belong to the alcohol type of chemical? Okay, cool. So we'll leave this here, and then the next video we'll have a little bit of an introduction to each of the different types of functional groups that you need to know, and each of the different types of families of the chemicals that you need to know.